Button in 3, 2, 1.
Hey, good evening and welcome to the October 2021 meeting of BayLISA, the Bay Area Large Installation Systems Administration User Group. My name is Mark Rovner and I'm the current president of BayLISA. We also have here today fellow BayLISA board members Peter Downs, Guy Purcell, and Dan McQueen. BayLISA is held on the third Thursday of every month and its meetings are open to the public. While the world might possibly be pulling back from the pandemic, social distancing is still a thing, and it's not right for BayLISA to resume personal meetings. So BayLISA will continue to be held in this virtual form until such time that not only us, but the companies that kindly offer us a space to do it in person feel safe. We hope you will continue to stick with us through this and join us in these virtual meetings. With the virtual format, we have been sticking with a few new rules. To that point, we expect everyone here has read the email that went out with the link to this meeting. Just a quick summary, please keep your audio muted. Feel free to ask questions in the chat, which we will present to the speaker at appropriate moments. And please be courteous and professional in any voice, chat, text messages. The meeting will be recorded and posted for later viewing on YouTube. BayLISA is a membership organization, and while it's not required, we do encourage people to join. Membership fees enable us to pay for various organizational expenses like domain fees, website fees, meetup.com fees, and such, so that we continue to bring you the best speakers with relevant and interesting topics. So to continue these events, we really do need people to step up and become members. Individual membership is $45 a year. Corporate membership is $2,500 a year. If you or your organization would like to become a member, please contact myself or one of the other board members in chat or later via email. BayLISA is a volunteer organization, and as such, the BayLISA board is always looking for volunteers. If you enjoy these talks, we do encourage you to give back to the community and help. It's not hard work, but shared work is always easier. The board meets the first Tuesday of the month, currently also via video chat, to plan for future general meetings and discuss other ways to make BayLISA better. Importantly, though, is finding speakers. So even if you don't have time to volunteer, but maybe you know of a topic or a speaker you'd like to hear, or even something you would like to present at BayLISA yourself, please tell us and we'll follow up. Again, please contact myself or one of the board members here, chat or email, or even via the meetup.com site. Normally, we take some time to thank our host for allowing us to use their facilities, but instead, we would like to thank each of you for taking time from your lives to bring us into your homes and spend it with us. While we can't provide food or drink in this format, we do encourage you to go get a quick drink or snack if you don't already have one. So hopefully we can feel a little bit more connected knowing we are temporally, if not spatially, sharing an experience. Somebody's audio is live and causing static. If you could mute yourself, that'd be great. Thank you. We typically reserve some time for announcements. First up, are there any BayLISA board members that have announcements they'd like to make? Okay, I'll take that as a no for now. We reserve a few minutes for job announcements. Even though lockdown pandemic is still going on, there are still people looking for jobs and still companies looking to hire. So if you have a job that your company is looking to fill, or you're looking for a job yourself, just ping us in chat and we'll unmute you to give a quick chat. I know last time you didn't have any, Guy, but are there any jobs over there at LinkedIn you want to talk about?
LinkedIn always has jobs, almost always. We're growing. My team has nothing though. There's nothing that I know of inside of systems itself, but I do know that various SRE teams around LinkedIn are hiring. So yeah, if you are interested, feel free to ping me for sure. You can just do it in chat. We'll make sure we sync up before the meeting closes.
Besides being BayLISA president, I also happen to work for Apple. I work on the team that manages the servers that Siri actually runs on. And we're a DevOps organization. We're looking for some DevOps-y-like folks. We deal with cloud services, Kubernetes, Linux, particularly Ubuntu, a bunch of Hadoop stuff and AML. If you're interested in doing that kind of work, it's a lot of fun over here. I'm a Linux guy, but I somehow wound up at Apple. You can also contact me via the chat or email or the website later. If anybody else has something they'd like to say, now it's time to give us a little ping and chat. Or we'll move on. We typically reserve a little bit of time to talk about upcoming tech events. Unfortunately, I don't know of any right now. All the really cool things like SRECon and KubeCon and AWS stuff, they've all kind of come and gone. They last week, it all seemed to come at once at us. If anyone else happens to know of any interesting upcoming tech events, again, give us a little ping in chat. We'll unmute you and talk about it. I do know that SRECon 2022 Americas has just opened their call for papers. So if you have something interesting in the SRE world, DevOps world that you'd like to share, now's your time to volunteer to present there. Okay, I don't see any volunteers, so moving on. One final note before we get started, we are looking to hold our regularly scheduled short but cool sessions December, but to make that work, we need folks to volunteer to speak. We're looking for about 3 to 6 short 10 to 15-minute talks about something cool and as it relates to the field of system administration engineering. Found a new way to install Kubernetes on your smart fridge? Do you have some tips or tricks on how to control all the things? Are you working on a personal container project that will blow people's minds? No time like the present to share. So contact myself or one of the board members and we'll schedule a slot for you in December. Okay, so now on to the good stuff. Data, it seems to be everywhere and nowhere at the same time. Keeping copies of everywhere can be prohibitively expensive, but when someone needs their data, they need it now and they want it close and fast to them. We've had mirroring, replication with dedupe, just to name a few of the strategies used to keep copies of data close to and fast to the consumers of it, each with its own strengths and weaknesses. Rather than keeping multiple copies in check, an alternate solution is being proposed tonight to leverage a typically LAN-based method over the WAN to deliver files on demand from anywhere without all the copying. So tonight, with his talk using RDMA over WAN to enable real-time access to dispersed storage systems, please help me welcome Steve Wallow with his talk.
Hey, thanks, Mark. So I don't have Kubernetes for the fridge, but we will definitely give you something else to work with here. So what I'm going to do, let me go ahead and share my screen, and we'll go ahead and get through this here. Okay, so what I'm going to do today, so this solution is something that most people don't think is actually possible, or they just don't believe it, is in the industry and it actually exists and it's been around for a while. So what I'm going to do is I'm going to show you the problem that the tech has actually been out to solve. I'll show you our approach to it, which is very, very different. The best way for me to kind of remove that hesitation of does this really work and does it exist is to show you a demo. So I'm actually going to spend a little bit of time. I'm going to show you a couple of demos. You can see it work. Then we'll talk about how we actually do this. And I think that it's important how we do it, but it's also important of how you can drop it into an architecture, right? I always tell people I can give you the greatest thing since sliced bread, but if you can't do something with it without having to completely change your entire architecture, there's really no value behind it. Okay, and then we'll finish up with a couple use cases. I am going to go ahead and mute my video here just to save some bandwidth. Let's see, I can do that here. Okay, so first and foremost, this is really the problem that we set out to solve. And Mark kind of alluded to this, which is, I have data that's being created all over the planet. Yeah,
we lost your screen share.
Oh, okay. Hold on one second. All right. Can you see it now?
Yes, we can see it now. Yes, thanks.
Okay, fantastic. Thank you. Thank you. So this is really the crux of the problem, right? It's that data is all over the place. It's being created normally at the edge, but is it really where it needs to be when you want to do something with it, right? It's the conundrum of maybe I'm using compute in the cloud, maybe I'm using compute in a data center, but my data is actually being created somewhere else. So I end up fundamentally just moving things around, right? And the reason we do that is this traditional thing that's been around for a long time, which is in order to get the performance from my applications, right? In order to get a good user experience, my data has to be somewhere by the compute. And what we've done through this technology is fundamentally change that paradigm. I'm going to show you how you really don't have to co-locate data and compute anymore in order to get performance. Okay. Now, if you look at some of the traditional approaches, and this is more along the lines of what this technology is not, but if you look at the things that people try to use to solve this problem, it's really one of two things. One is let's try to do some WAN optimization, right? I'll compress the data, I'll dedupe it, I'll make the data look smaller, the content look smaller, so that fundamentally when I move it, I'm moving a smaller subset, and theoretically it should move a lot faster, okay? The other approach, and more modern approach, is, well, let's put some intelligence behind that. Let's say, okay, I see your data patterns. What I'm gonna do is I'm gonna try to predict what you need ahead of time, and I'll move copies again and position them so that, you know, when you get in the morning, my data's there. These things fall apart for various reasons. One is if the data changes too much or it's too large in nature, then what happens is by the time I move copies to where I need it to be to use it, it might be stale, right? There's a perishability associated with the data. And of course, and how long does it take, right? The other part though is, you know, is it safe? Am I allowed to move it? In some cases through compliance or regulations, you know, I'm not actually allowed to move the information. Maybe I don't want to put it in the cloud. Maybe I can't have it leave the sovereignty where it's created. And all these things are really what we set out to solve and change. And our approach is completely different than the WAN optimization or the caching kind of thing. Our approach is really a two-headed coin here. One is if I just need to move the data, backup, coup, migration, standard table stakes, then let's find a way to move it faster than anything else that's ever been seen before. But what's really cool is in the process of creating this speed, we realized that we can do something kind of unique. And what we've figured out is we can actually have compute in one location, execute on data where it's created over large distances. The idea is to keep the data where it sits and not move it, but actually use the WAN, this high latent long distance WAN, in a way that you actually get the performance of a local area network. And this is kind of where people, you know, they turn their head a little bit and say, you know, I don't think this is possible. I would have heard of this. And I'll take a little tangent here and say the tech has been created, you know, a couple of years ago, specifically for the intelligence community and the federal government to do this type of thing. So there's a sensitivity originally around exposing this kind of technology. Vicinity was created to take this tech and bring it to the marketplace. So this is out there, it's robust, it's stable, and it works, but it is changing the paradigm of, do I have to have my compute, my data beside each other in order to get the performance, okay? So what we're really after here before I show you the demo is this. The idea is that from an enterprise perspective, I want to pick the compute of choice. Maybe it's the cloud, Amazon, Azure, Google, it doesn't matter to us. Maybe it's prem, it's colo, it can be edge compute. The idea is use the compute or compute sources that you want that make the most sense for your business requirement, but have it immediately work in real time on data wherever in the world that it's created. And we want to make sure that you don't have to change things in the architecture to make this go, meaning it can work on any kind of transport, satellite, internet, dedicated links, 5G, doesn't matter to us, right? But the idea is I'm going to take all of this stuff throughout the globe, whether it's my compute or my data, I'm going to make it all look like it's in the same four walls of a building with that local kind of performance. So that's really what we're after here. And the idea is that maybe I can federate the compute. You know, if you look at the title here, right? I want to be able to federate the resources. I want to do it on a global scale, and I want to be able to bring things in and out. That's really what this is about, okay? So this is different. So here's what I'm gonna do. I'm actually gonna show you a demo with a couple different things, okay? We'll walk through this. Now, the best way for me to show a demo is to show a comparison. So in this case, I'm actually using AWS for my compute. Specifically, this is AWS on the West Coast, right outside of Santa Clara, okay? Now, I'm gonna show you a comparison, okay? We're gonna run these things side by side. So I actually have two instances that are created in Amazon. One is going to be doing things using the vicinity method of stuff. The other one is the more traditional thing, and you're going to see these run, simultaneously. So that's where my compute, that's where my applications are on the West Coast. However, my data is actually on the East Coast. It's actually in one of our regional offices right outside of Washington, D.C. in Germantown, Maryland. So I'm separating my compute data by essentially East Coast to West Coast, almost 3,000 miles. What I haven't done is I haven't taken a copy of the data and cached it, pre-moved it, done anything like that to get it close to the cloud. I'm literally keeping them separated by 3,000 miles, okay? Now, it's the same exact instance type, the same exact network. The only difference, and you can see these by the little blocks here in the middle with a, the little V there. Okay, so the way the portfolio works, it's just essentially a virtual machine. We can throw some hardware assist at it, but essentially it's a gateway function, right? So I have one instance of our portfolio by the compute. It's kind of a bookend approach, and then I have one by the data. Okay, so the only difference between these two instances is that one is just tunneling through our VM in and out the door with the WAN in the middle. Other than that, it's the exact same network, exact same data, exact same instance types. Okay, so let me go ahead and show you the demo. So what I have here are two windows. This is just a remote desktop session. I'm logged into the vicinity instance on the West Coast. Now, the way the tech presents itself, it looks like a NAS device, okay? Standard files, folders, and shares. I will tell you, just for some future stuff, probably in the next 30 days, we'll have objects as well. But for this particular demo, I'm doing files and shares. So what you're looking at is the metadata, right? Or the pointers of the physical data that's still on the East Coast. But the good thing behind this is it looks like my data's here. So any applications that are running in this particular resource pool, and again, it could be data center, it could be anything else, but in this case, it's the cloud. Any application, as long as it can work with a standard network map share like you see here, it can take advantage of this service. Okay, so you don't have to make any changes to the application to take advantage of this. So that's what you're looking at here is the content on the East Coast. Now, I also have the more traditional approach here. You can see it's the exact same content. So here's what I'm gonna do. I'm gonna show you 3 different things and just kind of get the handle on things here. So first, what I'm gonna do is I'm actually just gonna move a file. And again, that's one side of the coin, but there's a reason I'm gonna show you this. So what I have here, I have a 5 gig file, just random numbers, nothing super interesting. And I'm just gonna drag it from the East Coast up into the cloud on the West Coast. So I'll go ahead and make that go. And what you're seeing here is it's gonna run 5-6 megabytes a second. It's pretty good. It's a nice clean link. It's kind of what you'd expect. If I do the exact same thing on the vicinity instance, same file, same network, same instance type, instead of 5 or 6 meg, what I'm getting here is a drastic difference, right? You're seeing 140, 150, something like that. Okay, so it is much faster. Again, if you just want to move things, we're gonna do that better than anybody. But the reason that I show you this is because we actually have a carve out where there's a certain bandwidth associated with what we have here. And what you're seeing that we can actually sustain over distance is equivalent to about 90%, 95, almost 93.5% of the bandwidth that's afforded for me to use. And if I can fill and sustain over distance, 90+% of the bandwidth, that's essentially a local area network. But I'm doing it using a WAN. So what we affectionately do is we call that, we've created a global local area network. And that's what's kind of unique, right? A lot of people say, well, I can fill a pipe, I can have a port, I can throw a pile of stuff in it. Sure you can, but when you get out over distance, it's kind of dribbling out the other side. And what I showed you is that I can, if I put in 9 gig out of a 10 gig link, I can get 9 gig out 5,000 miles away. That's what's different. We'll talk about how we do that, okay? Now, let's do something, so what can I do with that? Let's look at it from the application perspective, okay? Now, we're app agnostic, as long as it works with files, folders, and shares, and pretty soon your objects, then I can take advantage of this unique kind of capability. So what I have here, this is a 3D modeling tool. I'm going to show you. It's specific to seismic survey data, right? For example, a boat goes out in the ocean, they do a sensor sweep, and they take a look at the geographical, the different rock strata underneath, and they decide if there's oil there or not, right? It's pretty simple stuff. Works on layers, kind of like AutoCAD. So here's what I'm going to do. We'll start on the traditional side. Now remember, this application, its associated compute is in the cloud on the West Coast. but my data's on-prem. So think about what I'm saying here. Now we can run compute in the cloud against data on-prem. I don't have to move my data up to the cloud to be able to use it. That's kind of different, okay? So that's what I'm gonna do. So we're gonna go ahead and pick a 3D layer, and we'll just say add. We'll do the same thing on the vicinity side. Now, at this point, what's coming up are the different layers of this particular survey that I'm interested in. We'll just select them all. So we'll do that on the traditional side. We do the same thing on the vicinity side. And what's going to happen is, on the vicinity instance, the checks come up. And what's happening now is I am literally doing 3D rendering where my data and my compute are 3,000 miles apart. But the great thing is I'm getting the same user experience as if I had already taken the time to move the data close to the compute. And without vicinity, this is what you'd see, right? You see the spinning disk, and the checks will come back, and I'll hit OK, and it takes about another 20 minutes. I'm not going to wait for that. But the idea is that, if I can get this stuff in real time, then a couple of things change, right? One is if I have traditionally 10 people that want to do analytics on this data and in different locations, well, now I have to have 10 copies. And the more copies I have, the larger my attack vector, the more storage costs. I have to have 10 storage platforms to put this thing in, and which one is real and which one is not, and how do we correlate all these things? You can see the fundamental problems. That all goes away when I can work off a common data set in real time, okay? So I did want to show you that. Now, the other thing I'm going to show you one more application. We're not going to wait for this thing to finish, waiting for the paint to dry. We're going to do something with video. So, we did the World Series a couple years ago. They were kind enough to give us some of the content. In fact, let me go ahead and bring this up here. The idea is that it's one thing to do something with 3D elements. It's another thing to do something with live video. So what we're going to do is we're going to take these. I'm going to go ahead and set this demo up here. Apologize for that. We're just going to play it, right? So this is Adobe Premiere. We do a lot in the media entertainment space where moving content around becomes costly, but there's if I'm working on the next Marvel movie, the more copies I have floating around, the worse things can get. So this is again the World Series of Cubs interview. So I'm just going to take and play this video. I always ask who's a Cubs fan, and nobody ever replies. So I'm not going to go ahead and go through there. There we go, waiting for this to go. Okay, so because we're in a GoToMeeting and some other stuff, what I've done is I've turned on dog ears, and fundamentally what this does is it tracks the frames. That's what you see here as total and dropped. So what I'm going to do is I'm just going to play this Cubs interview. Okay, so I'll go ahead and hit play, and this is on the traditional side. Remember, again, this app Premiere and its compute is on the cloud on the West Coast, but my content is still on the East Coast. And what you'll see once this starts is I'll have my total count go up. There we go. But I'm also starting to drop frames, and you can see the video gets jittery, it's behind. If I had to do any kind of editing or any special effects or anything related to this content with this experience, it'd be horrible, right? That's why traditionally you move information around. Well, if I do the same thing over here on the vicinity side, let me bring this over here. There we go. I'm just going to drag this guy, whoever he is, over here. You see the same thing, right? The total and dropped. I'll go ahead and hit play. And all of a sudden, I'm having a different experience, right? I'm getting essentially real-time video playback without dropping any frames. In fact, if I tried to actually scrub around, that's what this line does in the middle. If I move it around and click, you can see how we're kind of waiting for the guy to move his head. There we go. Okay, right? If you had to do anything with it, that's a horrible kind of thing. But over here, all of a sudden, we have a real-time experience. Okay, so the idea is that, again, I want to be able to create an environment where my data, regardless of the location, looks and feels and performs as if it was sitting right beside me. Okay, so that's what's different. So let's go ahead and talk about, okay, how do we actually do this? How do we get around latency and all these things? We'll talk about a couple of use cases. So here's this is not what people say. Well, what did you do? What's the silver bullet to make this go? And it's not one thing that we've done. It's a combination of 30 plus patents and all put together to create a solution to solve this problem. And you not only have to address the network and latency and all these things, but how do I get to it from an architectural perspective? What about the storage? So I'm going to walk through some of these. I'm just going to give you some of the highlights, okay? Now, fundamentally, one of the first things we did is we changed the protocol stack, right? If you think about, TCP, right? It's perfect in the data center. You try to do that over long distances, and it's a very chatty protocol. When you add time and distance in the equation, you're waiting for answers, and it just creates a horrible experience over distance. UDP, which is the more traditional WAN optimization things, right? The idea is I'm just going to throw it on the wire, and then I hope it gets there, right? The problem though is you've moved, did it get there? It's responsibility to figure that out up the stack. And what ends up happening, and you kind of see this here between the blue and the green, is that for some of the other protocols, the majority of the bits that are flowing down the wire aren't necessarily the data, it's the overhead of the protocol to make sure that things got there, or other things. And that creates inefficiencies. And you can see here kind of on the chart where you have the performance on the vertical and the distance on the horizontal. Once you start throwing some distance in, the performance tanks, right? You can't sustain the distance. So what we did, and you see this as the V on the top line, is we went to the high performance computing industry. We said, okay, these guys are really good at figuring out how to do very fast, very efficient, very low latency transfers between computers, right? Think of the things as InfiniBand fabrics or Rocky fabrics, right? It's, I think Mark alluded to it, it's remote direct memory access, RDMA, right? Memory to memory transfers. Very, very cool stuff. The problem with RDMA is you get outside of a campus, maybe 20 kilometers, something like that, and the protocol kind of falls apart. Some of the patents that we have is the fact that we can actually take RDMA and we can keep these queue pairs, we can keep that protocol alive on a global scale. So now all of a sudden I have a way to leverage a protocol where the majority of the bits are data, not necessarily the overhead associated with it. And that's what you see. And what ends up happening is, instead of the graph on the left, where you see a tank over distance, I turned it into this. And that's what you saw in the demo, where I can actually sustain the performance and keep it going over distance. We'll talk about some of the things like flow control and what happens if we have errors and stuff like that. But that's fundamentally what the protocol is about, right? And again, there's a lot of other things associated with it. I'm giving some high-level pieces, but the bottom line is I can create a LAN on the right-hand side where a traditional WAN is on the left-hand side. Okay. Now the portfolio, it's just a speeds and feeds. You can everything from a VM to a hardware. So, we're not going to talk about that kind of stuff. We can talk about that later. But there's a lot of different options behind it. Now, here's how it integrates, right? Because this is one of the most important pieces. Is okay. So I see what you're doing, right? You've created kind of a nice little protocol. And oh, by the way, just so you guys understand, it is RDMA. But what we've done is we wrapped it in an IP header so that it looks like standard IP network traffic. So you don't have to change the WAN transport in the middle, right? As long as it's IP, we just look like everything else, right? So that's one thing that we wanted to make sure how to do. Now, the idea is that, it is a bookend approach. One can talk to many, but the idea is that each location, because it looks like a NAS device, if I have 10 users in a location, I don't need 10 vicinity things. I need one. And so give me a VM, put it on a server. It's not in line. It's just something that sits in the architecture, and people do mounts to it, right? They create network shares to it, so that I don't have to have all these, software licenses floating all over the place. And literally, it looks like a NAS device. So there's no changes to the software, no application changes except for file open, you just point to a different folder, okay? And then what we do is we terminate those standard TCP, NFS, SMB, CIFS kind of things. We turn it into that RDMA thing that we talked about, right? And I'm going to expand on that a little bit. And then what we do is we just reverse it and turn it back into standard files, folders, and shares on the other side. So one of the best things behind this capability is that to the endpoints, it's just stuff that they already know how to do. Files, folders, and shares. In the middle, we do our magic, but we make it look like IP. So you don't have to change really anything in the architecture to take advantage of that. That's one of the things we spend a lot of time with. Again, there's no compression or dedupe, right? This isn't about caching. This isn't about compressing. This isn't about dedupe. That's all the old traditional stuff. Because it was created for the government programs, some of the caveats were, hey, my data can be encrypted, or it's high-res video. I don't want artifacts if you start messing with it, because it's not humans that are looking at it. It's AI, ML kind of engines, and they can be susceptible to these kinds of things. So don't touch the data. So that's one of our overarching things. Now, before I go to the next step, let me explain. This is usually where people say, okay, I get you using RDMA, but you're saying you're not moving the entire data set. So what are you moving and how do you get around latency, right? That's usually something along the lines of the questions at this point. So let me talk about that a little bit. One of the things that, and I'm sure you guys know this, right? You know, when an application comes up, you kind of saw that on the demo, right? Whether it's Premiere or that 3D modeling tool, a lot of times the app is only looking for a component of the larger data set. Maybe I have a 100 gig file, but the app is only looking for, 10 gig at any given moment. And as the app walks and does its thing, maybe I'm moving different chunks, but I'm not taking the entire 100 gig and dropping it in memory. I'm only moving the pieces of interest per application that it wants to see. Well, we happen to have a file system that's distributed through all these locations that has the ability to see that. And what will happen is the local vicinity thing of the portfolio in the environment will say, oh, the app is looking for this piece, great. We'll push that request out to some remote location. We'll grab just that chunk of interest. We'll turn it into that RDMA memory-to-memory thing, wrapped in IP, we'll move it across. So what ends up happening is we're only moving the selected pieces of interest. So it's very, very efficient. And we'll do some read ahead things like that. So that helps us with kind of the sovereignty pieces. So a lot of times people say, hey, I'm an oil and gas, I have a terabyte file, but I'm only interested in this 10 gig. In the past, you had to move the whole terabyte to get to it. Now you only look at the 10 gig, right? So that's where some of the efficiencies come in. Now let's talk about latency. So as you saw in the demo, we can sustain LAN throughput over distance, right? We're pressurizing that link per se. So what ends up happening is when I go out and I grab that chunk of data, the very first bit that I get back, the very first bit will always incur the physical latency of the link. That's physics. We can't get around that. We're trying, but we can't get around that. If it's 70 milliseconds, you have to wait 70 milliseconds for the first bit. But because I can pressurize it, I can essentially make it a LAN, what happens is the second, the third, the fourth bit, everything after the first bit has that 90+% pressurization. So it's essentially a LAN after the first bit. And the beauty behind that is most applications, and I'll talk about ones that don't, but most applications can tolerate that little bit of latency on the first bit, as long as it doesn't show up all over the place, kind of like you saw in the Adobe Premiere demo, just kind of randomly showing up. So yeah, I have to wait an extra 70 milliseconds to start rendering, but that's okay. I can tolerate that with most applications. Now, there are some, especially in the some of the machine learning, the deep learning types of models where I need to have everything in memory, right? At that point, well, use the other side of the coin where, remember, we can just move stuff from A to B very, very fast, go entire data set. That's what'll happen. So you get the benefits of what makes the most sense for the application. Do I want to have that reach in, execute over distance? Or do I want to just move the data as a whole so that everybody can work on the consolidated pieces, okay? Now, the last piece I'll show you here before we go through the last two use cases is, what about security? So because we have a distributed file system, it keeps track of the locks and all those kinds of things. It's a POSIX file system, but we can actually do encryption of data in flight. Sure, a lot of people can't, but we took it to the next level. And you see it go from 1 link to 3. So if you're afforded multiple connections, maybe I have 200 connections, or I have 2 satellite connections, or a combination of the other, it doesn't matter. Latency is irrelevant to us. We can normalize it, right? What we can do is we can actually take that flow of information and we can spread it or stripe it across these multiple links and put a unique encryption key on there, right? So what ends up happening is we've created an environment where if, let's say you have 3 links like you see on the illustration here, if somebody got hold of a link and its associated key, they only got 1/3 of the data. So we've created obfuscation in addition to just standard encryption. So there's some other cool things that we've done to make sure that, yeah, even though all of these things are connected together and you have real-time access to everything, you want to make sure that by policy, you can say, this guy can only see this particular piece of this site or none of this site and things like that. And oh, by the way, it won't encrypt and obfuscate in the middle. Okay, so I did want to show you that. Now, to finish it up here and then we'll open up for the questions, what does this really mean, right? I showed you in the beginning kind of the business value behind that, right? I have this big enterprise architecture globally, and now I can get connected to everything. I can move it around, or I can reach in and use it in place. One of the biggest places we see this is the cloud. Right? One of the biggest problems with the traditional cloud model is, oh, sure, I want to use Amazon, I want to use Azure. I got to move if I want to use compute, I got to move my data up there, right? I can snowball it for Amazon. I can do an outpost, but fundamentally, that's just a local compute. If I want to use a cloud, I got to move the data up. I have to co-locate my data with the compute, regardless of the cloud model. That fundamentally changes now, where just like you saw in the demo, I can have compute in the cloud against data on-prem, data at the edge, data anywhere, and get the same performance. And when you have people that say, look, my data changes too much, it's too big to move in the time that I have, or for sovereignty compliance, I don't want to use the cloud. I'd love to use it, but then I'll get my data. All of a sudden now you have a different alternative. Or, and we've actually done this where, maybe my data is in Azure, but for whatever reason, I want to use the compute in Amazon for a particular application choice. You can actually have one cloud with compute, another cloud with data, or any combination of the above. And that fundamentally changes things, right? We do a lot with in entertainment and example life sciences, where you might have a lab doing some genomic research, or even COVID now, right? Where they're collecting tons of data, but the data is not leaving the building, right? But they want more compute, they need to burst. So now all of a sudden they have an alternative where I can use the cloud compute, only move sections of interest. Once that instance goes down, unless I create a work product, it's in memory, all the data goes away, right? So you have different alternatives here. Now on the slide, what you're gonna see here in the middle is this 11 terabytes per gigabit. And what does that mean? So when we talk about just moving data from A to B, you saw that on the 5 gig file that I moved. What we have here is for every gigabit of bandwidth that you give to this vicinity thing, right? We'll move roughly 11 terabytes in under 24 hours. And the speeds are unprecedented, but what's really cool is there's a determinism and a linear scale to it. And what does that mean? That means if you give me 10 gig, I'll move 110 terabytes. If you give me 100 gig, I'll move 1.1 petabytes. We've done that, right? So you can go and create an SLA that says, if I have this bandwidth and this kind of data set, it'll take this long. Or if I have this time window and this much data, what kind of network do I need, right? As long as you have 2 of the 3 variables, you can calculate the third. The other part though, is it's very deterministic. And I'll tell you, when we did that 1 petabyte across the country, we actually ran that 3 different times. And it was like 23 hours and 40 minutes or something like that. And each time the variance between the runs was 2 or 3 minutes over the course of almost 24 hours. So it's very deterministic. You can create one of the biggest problems with moving data is how long it's going to take, right? It can vary. And all of a sudden that paradigm changes, right? So that's one thing I wanted to show you. The last one here, and we'll look up for questions, is, what about the edge? People say, well, compute on the edge, that it elevates, kind of what you guys offer, and that's actually untrue. What ends up happening with edge is that's just more data everywhere, right? And the more data in different locations, the more value that we actually bring. So what ends up happening is, what does this mean with edge compute, right? A lot of people are trying to define what microservices are running at the edge. I'll give you one example. We have a lot of customers that want to use the cloud to do ML AI workloads, and then want to do it on data sets at the edge that might be disparate in nature, meaning one might be a social media piece, one might be archives data, and one might be real-time data from an industrial platform, or real-time from whatever, right? But the idea is that each of these data sets is very, very disparate in nature. Well, what's cool is with that edge compute, I can actually take advantage of it and curate or normalize that data so that it has a commonality to kind of the mothership, so we can go ahead and use it, right? But the problem that has always been occurring is, sure, I can throw edge compute at it and I can normalize the data, but then I had to copy it to wherever my master compute was. And at that point, my edge is isolated or stranded. It might take a day to move it. It might take an hour. And in some cases, an hour is too long. The data's old, right? Now, all of a sudden, because I can hit those platforms in real time, I can complement edge compute and do real-time geo-distributed AI and ML kind of workloads, right? So it really kind of complements some of the stuff that's coming down the industry. Okay, so that's what I had from a presentation perspective. let me go ahead and stop this and open up for questions.
So if you have questions, just ping us in the chat and we'll unmute you to let you talk. If you're on the live stream, put your question in chat there and we'll relay it to Stephen.
Mm-hmm.
So I guess just to start off with questions, I mean, one concern I have with some of the stuff you're showing here, Steve, is so if I have 10 people trying to edit a 10 terabyte video file, that's now 10 times that 10 terabyte file system is being streamed, being transferred. And so, like, especially with the cloud and AWS, you pay for every bit that goes in and out.
Yeah. Yes, you're absolutely right. So, let me make sure you guys understand that. So when it's not a stream, I think you got that right. And that really brings up two issues. One is, you have to make sure that, you're maintaining the coherency between the sites, right? And it works just like if everybody was in the same data center, meaning the first person gets read-write permissions, the next person gets root, right? Unless the application does some kind of byte range locking, right? So we apply to the same types of things. So this is, in some cases, it's workload dependent. You have to be careful how you put this together. But yeah, I mean, you're spot on, right? The idea is that I got to maintain that coherency. I got to make sure that everybody's controlled and working off the same thing. Now, I will say that even though we're not based on caching, we can turn that on. It makes in some cases it makes some sense, and the file system will keep track of cache imbalances and things like that. So there are some subtleties to that. So Mark, did I answer your question, or was there a second part to that?
No, that's a good answer. That was one question. So Michael Villain, he has a question. If you could unmute yourself, we can ask it directly.
So object, yes. So right now, the current technology is essentially file based. Object, it's a little different. The file system under the hood, and I'll let you guys know, it's actually a scaled down version of IBM Spectrum Scale, the old GPFS that we've kind of obfuscated from the users. Scale was great. It's very powerful, but it can get complicated. So what we've done is we've created an environment where the users don't necessarily see that, but under the hood, it's taking care of all those types of things. So if you have an object store and the application wants to go after a particular component of that, it's smart enough to grab those pieces. And again, with object, it gets a little different because if you're writing, essentially creating a new object, and we're moving those things around. But that's something I'd love to come back and give you guys an update on what we've done with objects. It's a little early for that, so hopefully that gives you a little answer. I'm purposely being kind of shy with it because we really haven't baked all that kind of stuff out yet. Hopefully that makes sense.
That sort of makes sense because object storage is a whole other animal. Instead of having everything all in one, like a physical container, it's in separate little containers, and you're all carrying it to a storage facility one at a time. And you have to then take all those containers to your home and then reassemble what you put in all of them. And that's essentially what happens when you use object storage.
Yep. It is a different animal, and I'll tell you, we're actually working with one of the database companies out there that aside from just being able to run the database in the cloud against object on-prem or everything like that. One of the things that's kind of unique, and we're putting the final touches on it, is they have a kind of a clustering mode where I can federate the compute. Let's say I have in different regions in Amazon, or maybe in Azure and Amazon. And what would normally happen is you would have to have multiple copies and keep those things synced so that the federated cluster can be working on commonality, right? And now that we can work off a single data set, we've proven that you can actually federate your compute from a database perspective and have it work off a centralized object store. But the idea is, and you're spot on, where you have to maintain, which pieces are going in which direction, all that kind of stuff. And the file system affords us to do that. Again, it's a little early for us. I'd love to come back and give you some more information on that. But yeah, it's a little bit, it's definitely different than file, but it's actually better in some locations because keeping track of locks and all that kind of thing gets a little easier.
Locking? You're talking about locking?
Yeah, on the file side, yeah.
Unix is notorious for, like, we don't do locking. You have to do locking.
Mm-hmm.
So that's kind of like, that was another thing, is that you have files that are, if 3 people are trying to edit a video file, that can't be done even locally. They have to, it's one person checks it out and uses it and then puts it back.
Yep, you're absolutely right. And there are some applications which will do byte range locking, so different people can work on different sections. But yeah, you have to maintain that POSIX compliance where you're absolutely right. First person gets read, right, everybody else gets read, right? Yeah, good point. Thank you. Other questions?
Hey, Dan, do we have any questions on the live stream?
While he looks at that, I have one. You'd mentioned errors. What happens if you don't have a nice clean line, network connection between points A and B, but didn't address it, so I'll bring it up.
Sure. Yeah, no, that's a really good question, because people say, okay, you're not using TCP, so you're removing the goodness of TCP. And what happens if errors come online? So we do something that's a little different. Normally what would happen, let's say you send 100 packets, right? And packet number 10 was bad or something, right? And at the receiving end, it would say, okay, you need to do a retransmission, resend everything that was in the window, right, in the TCP window. And oh, by the way, everything that was in flight you lost, right? It wants to do a restart, and that's a very disruptive process. So what we've done is we do something similar, but we've changed the paradigm on it. Meaning, we'll actually put sequence numbers on the packet, so it's very similar to TCP. But what ends up happening is our bookends, right? The vicinity thing on one end, the vicinity thing on the target end, have the responsibility of the error correction. So we do 2 things. Let's say you sent those 100 packets again, right? The vicinity sender said, okay, here's 100 packets. The vicinity receiver at the remote end said, oh, I got 100 packets, but number 10 is bad. So what'll happen is, instead of sending a retransmission request to the original client initiator, we'll actually send a selective retransmission to the vicinity sender and say, hey, oh, by the way, I lost number 10. We'll hold things in the buffers. And the vicinity sender will say, okay, let me resend number 10 because I know that's bad. We'll grab number 10 at the remote end. We'll put it back in order, right? Because we're holding things in a buffer. We'll put it back in order and we'll release it. And the beauty behind that is that the actual initiator never saw a retransmission and never had to resend all that stuff in the window. And of course, when you start working on the WAN, people start increasing the window sizes, right? So all of that kind of goes away. So that selective acknowledge or selective retransmission allows us to very quickly recover from an errored state. Now, one of the other things we do is very similar to FEC, if you're familiar with forward error correction, right? Most people do that kind of at the bit level. We actually do it at the packet level. So you can tune it for different ratios. If you have a high error line, we can add more parity packets. But the idea is that in some cases, if you only lost a few packets or there's something squirrely going on with them, we can rebuild it at the target end without even having to ask for a selective retransmission of number 10 per se, right? So you can get a lot of combinations of different things. And that helps us with that error recovery perspective. In a lot of cases, if you have a link that has a lot of errors, we can be in the middle kind of trying to clean that up so to the ends it looks like it's a cleaner link. One of the other things that we've done, just kind of elaborate on that a little bit, is I'm sure you guys are familiar with storage area networking, right? Kind of that crediting technology. And we do something similar where we want to make sure that the data is going to get there and that it's not going to get dropped at the target end because the target's just not ready to receive it, right? It's going to get thrown in the bit bucket. So what we do is we actually wait for a credit to come back and that says, okay, now I'm ready to receive it. and oh, by the way, you can send me this much data, and that helps us kind of create that lossless network. So it's very similar to a fiber channel technology in terms of the losslessness, but similar to TCP, but we kind of changed it to make it a lot more efficient. Did that help answer the question?
Yep. No,
Okay,
good.
cool. Yeah. Okay, so let's see here. Paul
We have a
wrote.
question. Yeah, Paul.
Yep. Or actually,
If it's
go ahead.
Paul's saying there is if it's your product is GPFS based, do you present it as NFS v4 to users?
So that's an interesting question. So it really depends, right? If we are the primary storage, which means that we can actually map NSDs to our particular part of the portfolio, like our VM, right? You can have some storage there for caching if you want to use it. We can actually be primary storage if you want, or you want to say, hey, this is kind of tier 0 storage for what you want to share. In that case, NFS v4 is fine. If we're talking to third-party storage, so normally we would take an NFS export out of let's say a centralized storage pool, and to do that, we actually use a function called Advanced File Management, AFM. And currently, well, actually, I should say, as of 2 weeks ago, with we were in the beta program, and now they actually support NFS v4, where in the past they were only NFS v3. So we are in the process of working with third-party storage with NFS v4 because they just got out of the beta program, and the new 5.2 actually has that. That's actually a really good question.
Cool.
Mm-hmm.
So Dan, if you see more questions in the live stream, you'll just type them up. We'll ask them. But I have another question for you too. So
Sure.
the problem with RDMA, is it's a security risk. So you usually, if you did that in your local data center, you put it on a separate network and locked it down, and because you're having direct access to machines. So I guess a two-part question is, first of all, how are you getting RDMA on devices in clouds, because you're running on a VM, not actually a machine? And either way, do you have some type of controls of like what memory can be? Or what's the security risk of putting this RDMA access over the WAN?
Sure. Yeah. So a couple things. Now remember, what ends up happening is it's RDMA in the middle over the WAN, right? But to the clients and to the external storage on either end, it's standard NFS, SMB, and CIFS, right? And eventually object. So we're not writing directly into memory on a client. What's happening is we're writing into memory on our gateway portfolio, and then we're presenting out as standard NAS things, right? So it's not RDMA directly to the clients at the other side. Now, one of the other things that we can do is, because it's essentially, think of it as an IB fabric, even if it's one node or a Rocky fabric, one node on one side, one node on the other side. We can actually turn on routing so that we can control to make sure that all of the traffic that's in that particular element doesn't go across the WAN. The only thing that goes across the WAN is what's actually been asked for. So it's a pull technology rather than a push. So the idea is that we're not blasting, let's say you're talking to 10 locations. We're not blasting 10 locations with information they don't need or could compromise, right? We're waiting for that pull mechanism, and we're only moving the components of interest in that particular environment. And then you end up with the ACLs and the other stuff on the other side to make sure that it's approved. And then you can actually go in and you can kind of tune the portfolio to say, this mount point can be seen by these guys, but not this guy. So we try to help out some of those particular characteristics, right? We don't want to break the paradigm of security. We just want to augment it. Yeah, good question.
But your edge device in the cloud is a VM, right?
In the cloud, it's a VM.
It's a VM.
Yeah, so it's a VM in the cloud, but on-prem, it's a combination of you can either have a VM, or we can take the same software and throw an FPGA at it in a PCI card, or a small appliance and do some hardware assist. And when you start throwing the hardware offload, you can do a lot more unique things. But yeah, you're absolutely right. It's a VM in the cloud and then hardware on anything else, or VM at the edge. It really speeds up the discussion. Did you have another question there, Mark?
Well, and the concern that with RDMA was always that you didn't want that exposed to the world in general, because you're exposing the internals of your hardware to attacks, as opposed to, like, if you went through a protocol, they'd have to break through the protocol, they'd have to possibly, language and stuff, but this is actually direct access to memory, and it sounds
Well,
like we're
between
opening a Pandora's box a little bit.
well, not necessarily, right? Because you're not doing it to the end stations or the client. It's really our stuff in the middle. And then the fact that, we can encrypt it, it's an upper level encapsulation that we can do different things with it. So we've done some things, but if you get through the encryption and the particular protocol stack, and you work your way up the chain, and you have some kind of deep packet inspection, sure, you're going to be able to see it just like anything else that's out there, right? It's how you work through it in the stack and how you obfuscate that through the different layers. But it's the same thing as any other protocol that's out there, right? If you keep going up the stack, eventually you're going to find something of interest. But the idea is to put enough layers in there that it's very hard to do that.
Okay. Yeah. So we have another question from Vincent. If you want to unmute yourself, you can ask it directly, or we can ask it for you.
Sure.
Yeah. So say, for example, we have a third-party storage that's using RDMA locally. Can the solution, say, mount RDMA from the third-party solution and then present it across all the way to the other end?
Yeah, interesting. That's actually a really good question. So I'm going to give you two answers. One is, if you have, let's say, an HPC with a IB or a Rocky fabric, we can just drop in and extend that, right? And put routing and all that kind of fun stuff. So in that case, you are stretching it. But if you have, let's say, a storage device that a VAST or something like that, that's using RDMA or any over fabrics, which is essentially Rocky in a lot of cases, right? As it's kind of interconnect between the different modules. We're actually working with certain companies to be able to stretch that, because it's not so much that it's just RDMA, or we can take RDMA all day long and move it. But what you have to do is you have to tune the file system to make sure that you can keep more data in flight before acknowledgement, right? Otherwise, you're really not buying any performance. You're stretching it, but the performance is horrible. So the idea is you want to tune it for the WAN. So for example, I want to increase the block size. I want to increase the number of RPCs. I want to be able to put more data in flight before the acknowledgement, so that I don't get sucked down by all the different protocols. So yeah, stretching NVMe over fabrics, which I'm thinking you're referring to, is something we are pursuing with a lot of different vendors right now, which would be actually really slick.
Thank you.
Sure, good question.
Oh, cool. So we seem to be out of questions in the GoToMeeting room. Are there any questions left on the live stream there, Dan?
No.
No?
That's it.
Okay. So, thank you, Stephen. This was a really great presentation. We're interested in seeing what's going on. We've had some other people say, good presentation too. This was definitely eye-opening in how we can get data moved across our data centers faster. New technology is always interesting and fun. So we hope you enjoyed the presentation tonight. Please send us your email with thoughts, comments, suggestions on how tonight's event went for you. If you think of anything that you might want to see to improve it. We do have a talk scheduled for next month. The details will be coming shortly. Reminder, we are looking for volunteers for the Short But Cool in December. And well, thank you for joining us. We will see you all next month.
Great. Thanks, folks.
Thanks all.
Thank you, Stephen.
Thanks.
Thank you. Bye.